Alright. In previous lessons, we talked about thermodynamic analysis of phase equilibria. This time around, we're going to look at chemical reactions. So we're going to look at chemical equilibrium. So at equilibrium, at a given temperature and pressure, we say that dG must be, which is equal to mu1 dN1 plus mu2 dN2, and so on, must be equal to 0, where 1, 2, 3, and 4, and so on are the species that are present in our reaction mixture. Okay, where does that come from? If you remember, G is a function of T, P, number of moles of 1, number of moles of 2, and so on. And at constant temperature and pressure, you just say dG is partial of G with respect to N1, dN1 at constant temperature, pressure, and other moles. Let's call that alpha J, plus partial of G with respect to N2, dN2 holding temperature, pressure, and number of moles of others, species constant, and so on. So partial molar Gibbs energy, partial derivative with respect to number of moles is just a partial molar Gibbs energy. So this is G bar 1 dN1 plus G2 bar dN2, and we said that partial molar Gibbs energy is just the chemical potential. So that's mu1 dN1 plus mu2 dN2, and so on. All right. So let's apply that to a fictitious reaction here. Okay. First of all, we said at equilibrium, dG must be equal to 0. Remember, dG at constant temperature and pressure must be less than 0 for a spontaneous process. Okay, we talked about this earlier. And it is equal to 0. It's minimized. We say G is minimized at equilibrium. So dG equals 0 simply means G is minimized at equilibrium. Okay. So if you were to plot G versus extent of reaction, okay, as the reaction proceeds, this is G versus, let's say, X is the extent of reaction, then once it reaches a minimum value, okay, you've reached equilibrium. So this is the point of equilibrium right here. If you go further past that, the G will start to rise. Okay? So let's apply that to this fictitious example, a simple example. A plus 2B gives you C. So let's imagine the reaction advancing by a small amount dx. Okay, what that means, by that we mean that change in the moles of A would be given by negative dx, because you're going to be losing A as the reaction proceeds forward. Then because of the restrictions imposed by stoichiometry, this balance equation says for every mole of A you're going to lose 2 moles of B, then the change in the moles of B has to be negative 2 times dx. Okay, and again, so 2 times the change in the moles of A. So, and you have a negative there because you're dealing with the reactant. Okay, and we also say that for every 2 moles of B you lose, and for every mole of A you lose, you're going to make 1 mole of C. So change in the moles of C, d ends of C will be plus dx. Right? So we can rewrite our expression for dG then, okay, would be mu sub A, chemical potential of A, okay, d ends of A plus mu sub B, change in moles of B, plus chemical potential of C times change in moles of C. That's equal to 0 at equilibrium. We can replace d ends of A by negative dx. Okay, so there's your negative and there's your dx. I factored it out. Okay, and dNB would be negative 2. Okay, change in moles of B would be negative 2 times dx. I'm factoring out dx here. And finally, we say that change in the moles of C, d ends of C, would be would just be dx. Okay, so what I have here is chemical potential of the product minus the chemical potential of the reactant. Okay, so you can say that's the change in the chemical potential of the products, and the chemical potential as you go from reactants to products, dx. Okay, or delta G bar. Now, Since we're looking at equilibrium we say dg at constant temperature and pressure, the equilibrium must be equal to 0. So for a small advancement of the reaction, there should not be a change in G. So that means this this term right here must be equal to 0. So you have negative chemical potential of A minus 2 times chemical potential of B plus chemical potential of C must be equal to 0. So this expression right here must be 0. Okay. In general, we can generalize this for any reaction using this expression right here. This is nu sub I times the chemical potential of species I, sum over all the possible species involved in the reaction must be equal to 0. What is nu sub I here? That's the stoichiometric coefficient for species I. Okay, so in this particular case, in this particular example, we have nu sub A is -1. Okay, so it's just the coefficient in the balance equation, but you put a negative sign in front if you're dealing with a reactant, and nu sub B would be -2. Okay, coefficient of B is 2, and it's a reactant, and nu sub C would be +1. Coefficient of C in the balance equation is 1, and that is a product, so we use a positive value for the stoichiometric coefficient. So this is the condition for chemical equilibrium. When a reaction has reached equilibrium, this condition must be satisfied. Okay, we call this expression right here delta G sub R. The change, and this is called the reaction Gibbs energy. All right, let's take a closer look at that expression. All right, so since dg is equal to negative mu sub A plus negative 2 mu sub B plus mu sub C in our example, okay, this is really sum of mu sub I, and we call that our reaction Gibbs energy is equal to dx. Then this delta G sub R, the reaction Gibbs energy, is in fact what? It's just the derivative of G. Okay, this is really just the derivative of G with respect to x. Okay, so that's partial derivative of G with respect to x at constant temperature and pressure. So this is, in fact, this delta G that we are writing here is not really a change, it's really a derivative. Okay, it's a change at, per mole of reaction as the reaction advances. Okay. Now, chemical potentials depend on the composition, depends on what your composition of your mixture is, your reaction mixture. So this delta G sub R, the reaction Gibbs energy, actually depends on the extent of reaction, because as your reaction progresses, the composition of your mixture is going to be changing, the chemical potentials will be changing. Okay, so delta G sub R is really what the delta G. So this is what the delta G would be per mole of reaction. So it's actually a derivative, provided the overall composition. If you can imagine, you have a 1 mole of reaction happening in a very, very, very large container, so that even though you have a mole of reaction, overall the composition hasn't really changed very much. The mole fractions of each component is pretty much the same. Okay, then that would be the delta G. The expression here, okay, would be the delta G for that reaction, for that system. Okay, it's sort of like the instantaneous speed. Okay, your instantaneous speed is, if you say your instantaneous speed is 5 miles per hour, that doesn't mean you're going to be traveling 5 miles in 1 hour. That would be the distance you would cover in 1 hour if your speed were not going to change during that hour. You know, the same thing here. If the composition of the mixture would not, if the composition of your mixture would not change appreciably during that 1 mole of reaction that occurs, then this delta G would be the change in the Gibbs energy. All right? All right, so let's see what a plot of G, Gibbs energy, looks like versus extent of reaction for this simple reaction, A gas being converted into B gas. Okay, we're going to use the letter X to represent extent of reaction. Your textbook is probably going to use this Greek letter right here. It's the Greek letter xi. Okay, and if you want to see what that actually looks like, it's this one right here. Okay. So it's pronounced xi or psi in English or xi in Greek, modern Greek. Um, but to make things easy for us, let's just use the letter X for that. Okay. So let's see what happens to G. Start off, to make things simple, we're going to say pressure is equal to P naught. We're going to do constant pressure, constant temperature. Okay. And we're going to assign, we're going to use P naught as our constant pressure. So we have A going to B, and we're going to assume we just have 1 mole of A to begin with. We have 1 mole of A and 0 moles of B. Now, at any given time, you're going to lose you will have lost X moles of A and made X moles of B. So the amount of A would be 1 minus X moles, and the amount of B would be X moles. Let's see what our initial G value is going to be. G initial Gibbs energy. Again, formula for Gibbs energy is N sub A, G bar A, plus N sub B, G bar B. Right? Moles, sum of all the moles, each one multiplied by the partial molar quantity. So this is going to be, initially, there is no B, so this is going to be 0. And partial molar Gibbs energy of A will just be the chemical potential of A. And since it's pure A and it's in a standard state, at pressure P naught, that's mu naught A, and our N sub A is just 1 mole. Okay, so it's just going to be mu naught A. That's our initial Gibbs energy. Okay. Okay, so now what's our G once the reaction is advanced by an amount equal to X moles? Okay, so I have X moles of reaction. G would be equal to moles of A, again, chemical potential of A, plus moles of B at that point, times the chemical potential of B at that point. So that's going to be moles of A at this point then will be 1 minus X. Okay, and I'm just going to write that as mu sub A, and moles of B at this point is X, and G bar B, you can also write that as chemical potential of B. Now, since we now have a mixture of A and B, chemical potential of A, it will just be equal to its standard chemical potential, okay, at P naught plus RT natural log of P sub A, partial pressure of A, over P naught. And the chemical potential of B, this one right here, is just going to be mu naught B plus RT natural log of partial pressure of B over P naught. But what's the partial pressure of A here? Partial pressure of A, okay, partial pressure of A is equal to mole fraction of A times the total pressure, but our total pressure is P naught. Okay, so that means, what does this mean? Mole fraction of A is just equal to P sub A over P naught. It's just equal to the mole fraction of A. So we can replace this thing by the mole fraction of A. And similarly, this thing right here, we can replace that by the mole fraction of B. Okay? So that simplifies our expression a little bit. This is going to give us 1 minus X, put this in red, 1 minus X times mu naught A plus RT ln mole fraction of A plus X times mu naught B plus RT natural log of mole fraction of B. All right. Now, let me collect terms here. I'm going to put all the terms that have the standard potentials together, and these terms right here with the natural logs, I'm going to collect them in one place. Okay, so I'm going to have 1 minus X times mu naught A plus X times mu naught B So these two, I'm going to put them together here, plus, okay, I'll have this term right here and this term right here. Note that this has to be multiplied by 1 minus x, and this is multiplied by x, okay? So this is going to be 1 minus x times RT natural log of x of a plus x times RT times natural log of x of b. Why am I doing this? If you look at this closely, you've seen this formula before. Natural log of mole fraction of A times RT times moles of A, and this is moles of B times RT natural log of B. This is just delta G. This thing right here is delta G for mixing of n's of A moles of A and n's of B moles of B. So that's delta G of mixing. All right? What about this term right here? What does this thing look like? Well, let's see. That's going to be, let me rewrite that as mu naught A, mu naught A minus x times mu naught A plus x times mu naught B. And I'm writing it this way so I can collect x. So I have mu naught A plus x, okay, let me just write this way, plus delta G mixing, right? I'm just going to put everything together. Now, I can factor out my x from here. So this is going to be mu naught B minus mu naught A plus delta G of mixing. Well, what is this? This is chemical potential of B minus chemical potential of A. That's a change in the standard Gibbs energy, standard molar Gibbs energy. Actually, the change in standard Gibbs energy. So that's delta G naught for this reaction. Okay? Chemical potential of the products minus chemical potential of the reactants multiplied by the extent of reaction. So that's x times delta G naught R. And you add that to mu naught A, and you add that to delta G mixing. Okay. Now you'll notice, if you remember, mu naught A was our initial G, right? So your Gibbs energy is going to change by this much and this much. All right, so let's plot that. G versus extent of reaction. And we're going to go from x equals 0, where everything's pure A, to x equals 1, everything's pure B. So let's say this is mu naught A. So that's going to be our G initial, right? And let's say our mu naught B is lower than A. It doesn't matter. You can do it with higher, and the interpretation will be similar. Okay, so let's call this mu naught B. And if we were to plot G versus X, what we'll find is this thing's going to drop. We're going to reach a minimum. Okay, so this minimum value is the value of X at equilibrium. Okay, so where the minimum in G is, that is your equilibrium extent of reaction. Now, let's analyze this graph and compare it to our expression up here for G. If you look at mu naught A, okay, and mu naught B right here, if you take this difference right here, if you take mu naught B minus mu naught A, this difference right here is really nothing more than delta G naught for the reaction. Okay? Now, imagine a straight line going from all reactant to all product right there, that straight line. And let's say the reaction has gone to this extent right here, x1. So let's see what happens at x1. Well, if you look at your bisimilar triangles, you should be able to show that this thing right here is nothing more than that distance right there is just equal to x times delta G, x1 times delta G naught. Okay, that's this term right here. Okay, so that's x1 times delta G naught for the reaction. Why is that? So that causes your G to drop. Why does it cause your G to drop? Well, your delta G naught, as you can see here, we've assumed that your delta G naught is negative. Okay, chemical potential of B is lower than A. If we had our mu naught for B up here, then that would have been a positive number. It would have made your G go up. Okay, so you're replacing A by B, so that causes the chemical potential to drop. That causes the Gibbs energy to drop. And then, so if this, and if you recall, the initial value is mu naught A, right? So this thing right here is mu naught A, this value right here. So we've accounted for this and this. So what's the difference between the actual G and these two? It will be delta G mixing. So this gap right here is the delta G for mixing. All right? So if it were not for the delta G of mixing, you would have just gotten a straight line going from mu naught A to mu naught B. You would have got, you would have minimized your Gibbs energy of the Gibbs energy for your reaction mixture by just transforming everything into product. But what happens is it does drop, reaches a minimum, and once it reaches that minimum, you have equilibrium. Let's take a look at a plot of G versus X using MathCAD. Okay, I have it set up right here already. So to make things simple, let's just assume your delta G initial is 0, and delta G naught, let's say, is also 0. Here's the value of RT, 8.314 times 298 Kelvin. I'm not using any units here, okay, to make things easier to follow. So G of X, G as a function of the extent of reaction will be the initial value, which is 0, plus X times delta G naught, okay, plus 1 minus X times RT ln of 1 minus X. Now, where did I get this 1 minus X? Remember, mole fraction of A is just moles of A, which is 1 minus X, over total moles, which is moles of A plus moles of B. This is moles of A, moles of B, so X cancels out. So mole fraction of A is just 1 minus X. Plus X times RT, natural log of mole fraction of B. That's your mole fraction of B. Okay, so that's X over the total moles, which is 1 minus X plus X. All right, so if I make that plot, I'm going to plot from X equals 0 to 1 in steps of 0.01. This is what I get right here. Oops, let me get rid of all my annotations here. Okay, so what's the point of equilibrium here? It's around 0.5. So when the extent of reaction has reached 0.5, so you would expect your equilibrium here at equilibrium for the amount of A to be equal to the amount of B. Okay, so your equilibrium constant would be 1. Okay, so at equilibrium here, A and B would be equal. They would both be 0.5. Now, what would happen if my G were to become more negative? Okay, by the way, this will just be, you're able to achieve here the largest possible delta G mixing, okay, half a mole of A and half a mole of B. Now, what would happen if I were to make my delta G more negative? So let's say I made that negative 50. Look at what happens. It's shifting to the right. Okay, let me move this closer. And let's make that negative 100. Oops. Let's make that negative 1,000. The more negative your delta G naught, okay, this is your delta G naught, the more negative it is, the more your point of equilibrium is closer to your product side. So if you make this negative 10,000, That's really close to the product side. Let's make that negative 5,000, and you can see your minimum right here is close to the product side. So a negative delta G naught means the reaction goes farther towards the product side. All right. But what if I were to make my delta G naught positive? So if I make that positive, what happens? See, your point of equilibrium is going to be right here, closer to the reactant side. When delta G naught is positive, your reaction hardly goes forward. Okay, so if I make that a little less positive, let's make that 500, it can go a little further. So your point of equilibrium in this case would be right here. Okay, so that's how the Gibbs energy changes. Now, word of caution, this thing right here on our plot, okay, this delta G mixing plus X1 delta G naught, this is not the delta G of the reaction, okay? That's not the delta G of the reaction. The delta G of the reaction at this point is the slope of the tangent line to a plot of G versus X. So what we call delta G of the reaction is actually the derivative of G with respect to X at that point. Okay, so be sure you're aware of that. That's the delta G, what we call the delta G of the reaction, is not this difference between the initial G and the G at that point. It's actually the slope. It's what the change would be if at that particular point in time you would have the reaction would advance so that you get a mole of reaction without much of a change in the composition of the reaction mixture. Okay. Okay, so let's see what would happen to G versus extent of reaction for this reaction right here, where you have A plus 2B gives you C. All right, so what's going to happen is something like this. Let's say we start off with, again, we're going to assume we have a stoichiometric ratio of A and B to begin with and no C. So you'll just start off with 1 mole of A and 2 moles of B. So your initial Gibbs energy would be 1 mole times mu naught, mu sub A naught, plus 2 moles of B times mu sub B naught. That's before mixing, okay? Then once you mix the two, that is going to drop, all right, before any reaction can occur. Then what you have here would be, so this drop right here would be delta G of mixing. Okay, that's the delta G of mixing of your 1 mole of A and 2 moles of B. And then what's going to happen? Let's just say chemical potential is C of C is over here. Right here. Let's just say that's the case. So when everything's converted into C, so our extent of reaction would be 1 over here, 0 here, so mu sub C naught, okay, it's going to be pure C. So this one right here would be separated A and B, okay? Each one at P naught. And then you mix them, and then this one right here, you just have pure C. So what's going to happen is your Gibbs energy, we're plotting Gibbs energy here, is going to drop, okay, and eventually it reaches a minimum. So that's X at equilibrium, and then it's going to rise back up to there. Chemical potential of C, mu naught C. All right, so just as before, this difference right here would be standard Gibbs energy of the reaction, right? And if I were to draw a straight line between these two, oops, wrong one. If I were to draw a straight line between these, okay, I got the wrong, sorry, fix that. Delta G naught would be actually this one right here. So delta G of reaction naught. And if I were to draw this line right here, okay, then let's say when the extent of reaction is this much right here, let's say X1. All right. This difference right here, you should be able to show that that difference is just X1 times the standard Gibbs energy of the reaction. And then, but the total Gibbs energy, that raises the Gibbs energy, okay? But, so replacing A and B by C would increase your Gibbs energy. But then, this one would be the delta G for the mixing. So this is delta G for the mixing of A, B, and C. All right, so that's what that reaction, that Gibbs energy looks like for that. All right, so let's take a look now at an equation that you've probably seen in your freshman chemistry class. This equation right here, delta G for a reaction is equal to the standard delta G for the reaction plus RT times natural log of Q, where Q is what you would call your reaction quotient. Let's see where that equation comes from, okay? So we'll just use a simple example. You can derive this more generically, but let's use a simple example to make it easier to follow. Remember, your delta G is, we defined this earlier, that's the derivative of G with respect to extent of reaction, right? And so mu sub I will be the coefficients. So this is going to be, and mu sub I are the chemical potential. So in this particular case, you're going to say coefficient of A is 1, so -1 times mu sub A plus coefficient of B is 2, so -2. Stoichiometric coefficient of B is -2 times chemical potential of B plus coefficient of C is 1, so plus chemical potential of C. All right, so that's your delta G for this reaction. And I'm going to rewrite this. I'm going to say that's negative of -1 times mu A naught plus RT natural log of activity of A. Now, if this was pressure, since this is a gas, activity in this case would just be partial pressure of A over P naught, right? So I'm just going to make this generic. So I'm just going to call it activity of A because this could apply to aqueous solutions as well. All right, plus -2 times mu naught B plus RT natural log of the activity of B. Okay. Plus chemical potential of C, so 1 times mu naught C plus RT natural log of the activity of C. Okay, I'm going to combine all the terms that involve standard potential. So I have negative, okay, mu A naught minus 2 mu B naught plus 1 times mu C naught. So I'm combining this term, and this term, okay, plus all right, I'm going to say this is RT ln A sub A, activity of A, but there's a negative here, okay? So that's negative RT. I'm going to put that -1 over there. Remember, A ln B is equal to ln of B to the power A. So I'm going to make that a power, okay, later. Okay, plus -2 times RT, -2 times RT natural log of activity of B plus +1, okay, times RT natural log of activity of C. So I'm going to move this over here and move this over here. So this becomes, what is this right here? That's just standard delta G for the reaction. Delta G naught for the reaction plus, this becomes, I can factor out my RT, natural log of A to the -1, okay, plus natural log activity of A to the -1, plus natural log of activity of B to the -2 power, plus natural log of activity of C to the +1 power. Okay. And so this is delta G naught plus RT, natural log, okay, log identity, log A plus log B is equal to log of A times B, right? So I'm just going to say natural log of A to the activity of A to the negative 1, activity of B to the negative 2, activity of C to the positive 1. All right. Right, so you can see activities of reactants are raised to the negative power, and activities of products are raised to the positive power. So this gives us delta G naught plus RT natural log. I can write activity of C raised to the power 1 over activity of A raised to the power 1 times activity of B squared. And this is what you call your reaction quotient. Activity of products over activity of reactants, multiply them in the numerator and in the denominator, but raise each one to a power corresponding to its coefficient in the balance equation. Okay. By the way, you may see this expression here written as a product of activities of I raised to the power nu sub I. Okay. Product over all the possible species of the activity of each species raised to its stoichiometric coefficient. So reactants will be raised to a negative power, and products will be raised to a positive power. That's another way of writing that expression. So that's your Q. Okay? All right. So that's where that expression comes from. All right, so how do we determine the equilibrium constant? Straightforward method, if you recall from freshman chemistry, simply let the reaction go to equilibrium and then measure the activities of the species at equilibrium. KEQ will just be whatever the Q is at equilibrium, so you calculate Q. Okay, now you can show that there's another way you can calculate KEQ, and this one is by saying that, okay, at equilibrium, delta G is going to be equal to 0 at equilibrium, right? So if at equilibrium delta G equals 0, then you can say delta G naught plus RT ln of Q must be equal to 0 at equilibrium, but at equilibrium, Q is not KEQ. Q is equal to KEQ. At equilibrium, Q equals KEQ. So we can solve for KEQ here. Rearrange this. You can say KEQ would just be equal to, right? RT natural log of KEQ would be equal to negative delta G naught. Divide both sides by RT. Natural log of KEQ equals negative delta G naught over RT. And so KEQ equals e to the negative delta G naught over RT. So if you know the delta G naught for your reaction, you should be able to calculate KEQ. So this is where the connection is between heat measurements, something seemingly unrelated to the idea of equilibrium, chemical reactions and chemical equilibrium. This is the connection between heat measurements and equilibrium. Okay, if you recall, you can determine delta G, delta H, and delta H from heat measurements and delta S from heat measurements, and you can calculate delta G from those. Delta G is delta H minus T delta S. So if you know the standard Gibbs energy of a reaction, you can calculate its equilibrium constant. So let's apply that to this simple example right here. H plus hydroxide, aqueous gives you liquid water. Delta G naught for that reaction, you can calculate that from tables. You look up delta G formation of liquid water, delta G formation of hydroxide, and delta G for the standard delta G for the formation of H plus, which is going to be 0. And you calculate delta G for this reaction. We've done this earlier this semester. That's negative 79.89 kilojoules per mole. How do you calculate KEQ for this? KEQ would just be e to the negative delta G naught over RT. All right, and so let's do that calculation in MathCAD. KEQ equals e to the negative delta G naught, which is 79.89 kilojoules per mole. Negative of negative 79.89 times 10 to the third joules per mole. So, oops. So that's delta G naught over R, which is 8.314 times joule per Kelvin per mole times our temperature of 298 Kelvin, and KEQ should come out to be 1.00 times 10 to the 14. Okay? So here you have 2 decimal places. So this is your delta G naught. Okay? And this is your R, and that's your T. 2 decimal places. That means when I take the antilog, I should have 2 significant digits. So it's going to be 1.0 times 10 to the 14. And let's see what we have here. It's going to be 1.0 times 10 to the 14. Does that look familiar? That's just the reverse of the autoionization of water, remember? And what was the KEQ for this? We call it KW. It's 10 to the negative 14. So you reverse a reaction, your KEQ is just the reciprocal. Let's do full screen. All right. You can use a comparison of Q with KEQ to predict the direction of a reaction, whether it's going to go forward or reverse. All right. So again, let's start with delta G equals delta G naught plus RT ln Q. Since we've already identified delta G naught as negative RT times ln KEQ, we can replace that. And so what do you have here? You can combine these two, factor out RT. Okay, so that's RT times ln, negative ln KEQ plus ln of Q. So that's RT times natural log of Q over KEQ. Right? Is equal to your delta G. So that's another way of writing that relationship. So you'll notice that if Q is equal to KEQ, ln of 1 is 0, so delta G is equal to 0. What we're really saying is dG dx is equal to 0. Advancement or reversal of the reaction will not cause G to change, provided you have that infinitesimally small advancement or reversal of the reaction. Okay, you're at equilibrium. Okay, so that's your delta G. That's another way of expressing delta G. What happens if Q is less than KEQ? What would be the natural log of a number less than 1? Q is less than KEQ. Number less than 1 would be negative, right? So your delta G, in this case, is going to be negative, and so what will happen? We say if delta G is negative, then the reaction as written will go forward. So you say a forward reaction occurs. It's the spontaneous reaction. Another way to think about it is as you're going towards product side, your Q is going to be increasing, right? You'll have bigger numbers in the numerator, smaller numbers in the denominator. So Q will have to increase until it becomes equal to KEQ. If it happens to be less than KEQ, what will happen is the reaction will go forward until Q becomes equal to KEQ. Now, what happens when Q is larger than KEQ? Similarly here, you can say if Q is larger than KEQ, then this expression is going to be larger than 1. The natural log of a number greater than 1 is going to be positive, and then your delta G of your reaction is going to be a positive number. So that means the reaction as written, the forward reaction, is going to be non-spontaneous. Okay? So the reverse reaction will be the spontaneous reaction. The reverse reaction will occur. And So when a reverse reaction occurs, your Q will be dropping. Eventually, Q will become equal to KEQ. So when Q is larger than KEQ, reverse reaction occurs. Q will drop until Q becomes equal to KEQ. So you can use this to explain the Chatelier's principle. Just to remind you, the Chatelier's principle says if you have a system at equilibrium and you apply a stress to it, it will respond to the stress by shifting in the direction that counteracts the stress, okay? Shifting the point of equilibrium. Possible stresses you can impose on your system would be like can be really classified into two types. One that is something that causes a momentary change in your reaction quotient at constant temperature, okay? Or the other type of stress you can introduce would be a change in temperature. And this is the kind of change that would actually make KEQ change. So during that momentarily, then your K, in both of these cases, your Q will, the stress will cause your Q to be not equal to KEQ. And so the response of your system will be to make Q equal to KEQ again. It's going to shift either to the left or to the right. Reverse reaction or forward reaction until Q becomes equal to KEQ again. So let's look at a simple example. Let's say you have A gas turning into 2B gas. Let's say you have a reaction mixture with A and B already at equilibrium. What happens if we were to increase the total pressure at constant T? Remember what you learned from freshman chemistry? You increase the pressure, so the system will respond by shifting in the direction that would tend to lower the pressure, and the lower pressure is obtained by shifting to fewer moles of gas. So it will shift to the left. Let's see if we can look at that more quantitatively. The equilibrium constant for this reaction, we call that K sub P, right, is pressure, activity of the product, which would be activity of B, which is P sub B over P naught squared, coefficient of B is 2, divided by the activity of the reactant. The reactant is A, so partial pressure of A over P naught. Okay? So remember when in your freshman chemistry you were told the activities are given by the partial pressures. Okay? Then they're actually unitless. You have to divide the partial pressures by P naught. So what you have in your expressions are actually unitless quantities. Activities are unitless. All right, so let me rewrite this into something easier to follow. So P naught over PB over P naught squared over P sub A over P naught. Okay? We can express your PB as mole fraction of B times the total pressure, whatever it is, and then divide by P naught, and you get squared there. And partial pressure of A would be mole fraction of A times the total pressure. So you divide that by P naught, and what do we get for our Kp? This becomes equal to, all right, so you have mole fraction of B squared over mole fraction of A. So, and then you have P over P naught raised to the power 2 minus 1. Okay? So we call this expression right here, so it looks like a reaction quotient expression, but expressed in terms of mole fraction. We're going to call that K sub X. Okay, that's not really a constant. Okay? And this expression right here, P over P naught. And 2 minus 1 is really the change in the moles of the gas during this reaction. 2 moles of gas minus 1 mole of gas. So if you have a mole of reaction, then you have a change of 1 mole of gas. So this we're going to call this delta N gas. All right, so that is your K sub P. If the value of P and Kx you're using are the values of equilibrium. Otherwise, that will just be Q. So what would happen? So now you have a reaction at equilibrium. Okay. What would happen now if we were to momentarily cause the pressure to increase? How do we do that? We squeeze the gas, right? We make our pressure go up. So now suddenly this term right here is going to be larger, right? So since Kp is a constant, okay, you made your Q bigger. So if this goes up, then your Kx has to go down, right? So if your Kx has to go down, what does it mean? Then this denominator has to go up, and this numerator has to go down. So that means you're shifting to the left, as we expected. The system's response will be to shift to the left to have fewer moles of gas. All right. Now, if this reaction were switched, the conclusion you'll reach would be the opposite, because then your delta N gas would be a negative number. You'd have 1 minus 2 would be negative 1. All right. So you have to look at reactions on a case-by-case basis. But in general, your prediction that an increase in pressure will cause a reaction to shift to the side with fewer moles of gas, that would be generally true. That would be, this is how you show that that is in fact the case. Okay? All right. Let's talk now about the Van Hoff equation. The Van Hoff equation tells us how an equilibrium constant depends on temperature, and we can derive that from the Gibbs Helmholtz equation, which we saw in an earlier lesson, which says that the partial derivative of g over t with respect to 1 over t at constant pressure, okay, this really should be partial derivatives, is equal to h, the enthalpy. All right, and from this equation we can show we can derive the Van Hoff equation, because you can then say that the partial derivative of delta G, the standard reaction Gibbs energy, over T with respect to 1 over T must be equal to delta H of the reaction. Okay? So let's do that. We've already established that delta G naught is the standard Gibbs energy is negative RT ln K EQ. So let's make a substitution here. Derivative of delta G naught over T would be negative RT ln K EQ. That's delta G naught divided by T. All right, so T cancels out there. With respect to 1 over T, okay, is equal to delta H of the reaction. So if I were to rearrange this, I can say differential of ln K EQ is equal to delta H, and there's a negative there, so I'm going to put the negative on the right hand side now. So it's going to be negative delta H naught over R, so I'm going to move this one over to my right side, times differential of 1 over T. Okay. If we integrate both sides of this equation, we get ln K EQ at temperature T2 minus ln K EQ at temperature T1 is equal to negative delta H over R, okay, 1 over T2 minus 1 over T1. Now, this integration is valid for as long as we're looking at a temperature interval that's small enough so that delta H within that interval is more or less constant, independent of temperature. We're treating delta H here as an independent, as a constant. Right? So we can rewrite this as ln of KEQ2 over KEQ1 equals negative delta H naught over R 1 over T2 minus 1 over T1. Right? So you can see this is very similar to the Clausius-Clapeyron equation, and we'll talk in a little while why that's the case. So, but anyway, if in general then, if you were to just do ln KEQ versus 1 over T, what would be your slope? If you have 2 points, the slope will just be equal to what? If I were to plot ln of KEQ versus 1 over T. Okay, oops, my slope. Let's say I have that graph that looks like that. I have 2 points. So let's say this is ln of KEQ point number 1 and point number 2. That's my slope there. My slope is equal to ln of KEQ2 minus ln of KEQ1 over 1 over T2 minus 1 over T1, right? So that's just this one divided by that one. So just like the Clausius-Clapeyron equation. So that's equal to ln of KEQ2 over KEQ1 over 1 over T2 minus 1 over T1. So that's your slope. And so that's equal to negative delta H over R. So that actually allows us to, this is actually one way we could determine the delta H for a reaction. You measure the equilibrium constant at two temperatures, T1 and T2. The slope of this line, okay, or you only have 2 points, that would be the ln KEQ2 over KEQ1 divided by 1 over T2 minus 1 over T1 is just negative of the delta H for the reaction divided by R. So you can solve for the delta H of your reaction by just multiplying the slope by negative R. Okay? Now, I said earlier that it's very similar to the Clausius-Clapeyron equation. You remember your Clausius-Clapeyron equation? What was the Clausius-Clapeyron equation? Clausius-Clapeyron equation says ln of P2 over P1 equals negative delta H vaporization or sublimation over R 1 over T2 minus 1 over T1. Why is that? Well, look at it this way. Let's say you have a solid or a liquid A in equilibrium with gas, right? What's the equilibrium constant for that? If you think of that as a chemical reaction, then you say KEQ is just activity of A in the gas over activity of A in the liquid. Activity of A in the gas is just partial pressure of A in the gas, right, over P naught. And activity of liquid A is just 1. So you can say, you can plug in PA at temperature T1 as your P2 and PA at your temperature PA at temperature T2 as P2 and partial pressure of air at temperature T1 as P1. So it really is, the vapor pressure is an equilibrium constant, okay, divided by P naught. Okay, and then the activity of your liquid is equal to 1. All right, now we can also use this. All right, so okay, before I move on, so we say that if you plot ln KEQ versus 1 over T, your slope is going to be equal to negative delta H naught for the reaction over R. Okay, how can we use this to explain the effect of temperature on equilibrium? Well, let's say your plot looks like this: ln of KEQ versus 1 over T. Let's say it looks like this. Okay, we have a positive slope. Okay, so that's equal to negative delta H over R. So what's our delta H here? Delta H is going to be negative. We're looking at an exothermic reaction. Let's see. 1 over T, the value of 1 over T here is lower, so points over on this side represent high temperature. Points on this side would represent low temperature, right? And this is low KEQ, and this is high KEQ up here. Smaller log, smaller value of KEQ, a higher log of KEQ, a higher KEQ. So what is this graph telling us? The higher the temperature, the lower, okay, look at this, the lower the KEQ. Okay, in other words, if you were to raise the temperature of this reaction mixture, if you have an equilibrium, okay, and you raise the temperature of your reaction mixture, it will shift to the left. Okay, so according to this, higher temperature, okay, you'll get a lower KEQ. So if you have a reaction that's already at equilibrium, Q equals KEQ. By changing the temperature, you're lowering the KEQ. Q will have to follow to reestablish the equilibrium. So if you lower your KEQ, then there's going to be a shift to the left. All right. Now, what did we say Le Chatelier's principle says? Let's say I have a reaction A going to B, okay, and it's exothermic. So if it's exothermic, you say heat is produced, right? So according to Le Chatelier's principle, if you were to raise the temperature, okay, you're providing heat, you're raising the temperature, the equilibrium mixture will react in a manner that will counteract the stress. So if you're putting in heat, the direction that will be favored is the reverse direction where that heat is consumed. In other words, we say that the direction that is favored by adding heat to an equilibrium mixture is the endothermic direction. In this particular case, since the forward direction is exothermic going forward, the reverse is endothermic. So we're favoring the reverse reaction, you're lowering the KEQ, right? So you're favoring the endothermic direction, which in this particular case is the reverse direction because the reaction as written is exothermic. Now, you should be able to make an argument, similar argument, if the slope was negative, okay? If a plot of natural log of KEQ versus 1 over T is, if the slope is negative, is equal to negative delta H over R, then that means your delta H must be positive, then you have an endothermic reaction. Okay, so at low temperature over here, and you have high temperature here. So at high temperature over here, you have high KEQ. Okay, so that means high temperature, so this reaction will be favored, the forward reaction is favored by high temperature. So, and you can rewrite here, you can say heat, so it's an endothermic reaction, so you say heat plus reactant gives you products. Alright, so an increase in temperature, provision of heat to your equilibrium mixture will make the system react in a manner that will counteract that stress, so it will try to get rid of the heat that you provide, so it's going to shift to the right, higher KEQ. So let's now talk about redox reaction. If you recall, a redox reaction is a reaction that involves a transfer of electrons, and you can think of it as consisting of two half reactions. Reduction is the gaining of electrons, and the oxidation half reaction involves the loss of electrons. Okay, and we can carry out these two half reactions in separate compartments. Okay, and if we link up those two compartments, you can measure the voltage, okay, between the two compartments. You call them the half cells. The voltage that you measure is called your cell potential, okay? And if you remember, your everyday household battery is an example of electrochemical cell, okay? So you have a negative and a positive terminal, and the voltage between those two is about 1.5 volts. Right? That's an example of an electrochemical cell. Now, the cell potential allows us to determine delta G for the reaction. Okay? And delta G for the reaction, and the reason for that is because delta G for the reaction would be the maximum amount of work that you can harness from that reaction, non-pressure volume work. If you remember, we said the significance of delta G when we first talked about free energy functions. That's the maximum non-pressure volume work that you can harness from your system. That's allowed by the second law of thermodynamics. So what work can we generate out of an electrochemical cell? We are configuring our reaction so we can generate non-pressure volume work from our electrochemical cell. And that work is the work that pushes electrons from the negative terminal to your positive terminal. Okay, so the work involved in transferring electrons across a potential difference, okay, is equal to the voltage times the charge that's being transferred. Now the voltage in your electrochemical cell is your cell potential. The charge that's transferred, okay, let's do this per mole of reaction. Let's say you have n moles of electrons transferred when 1 mole of reaction occurs, then the charge transferred would be negative n, negative because the charge of the electron is negative, and F here is the Faraday constant. That's the charge of 1 mole of electrons. Okay, so the charge transferred is equal to moles of electrons times charge per mole of electrons. So this is Avogadro's number, okay, that's 1 mole of electrons times the charge of each individual electron. This would be the charge of 1 mole of electrons, so that's going to be 96,500, oops, this should be coulombs per mole, okay. So you multiply that by the number of moles, that gives you coulomb. All right, let's look at our units here. E cell is in volts, right, and negative NF is in coulombs. A coulomb volt, okay, 1 coulomb volt is 1 joule. All right, so that has units of energy. So delta G would be negative N times the Faraday constant times the cell potential. Now this delta G is dG dx, okay? Now, since delta G is delta G naught plus RT ln Q, we can equate that to negative NF E cell in this equation right here, and we can rearrange this to solve for E cell. E cell would just be, okay, I'm going to solve for the cell potential, so it's just going to be delta G naught divided by negative NF, that's what you have right here, and minus RT over NF times ln of Q. All right, so that's your cell potential in terms of delta G naught. Okay. Now we can define this term right here. We'll define this as the standard cell potential. Okay, and so E naught cell, E cell naught would be your standard cell potential. That's related to your delta G naught over NF. Now earlier we said if we know delta G naught, we can figure out KEQ. So what this means is if we know the standard cell potential, we can figure out delta G naught, and so if we can figure out delta G naught, we can figure out KEQ. This equation, by the way, okay, is what is known as the Nernst equation. You've learned that in your earlier courses, all right? So we can, at 298 Kelvin, all right, and so that's at room temperature, this RT over NF and this natural log, you can change that to a base 10 log. If you do that, you can replace that by 0.059 over N times log of Q. So that's another form of the Nernst equation that you may have encountered. So the question is, how do we determine the standard cell potential? Well, we can measure the cell potential, right? So how can we make that equal to the standard cell potential? We just make this term equal to 0. Okay, how do we make that equal to 0? We set up an electrochemical cell where Q is 1. Okay? So if we set up an electrochemical cell where Q is 1, or find a way to set up a series of cells so that you can extrapolate or interpolate to the situation where Q is 1, you get the value for your standard cell potential. Because whatever cell potential you measure at that point will be your standard cell potential. So given that, we say now that delta G naught is negative NF times standard cell potential, all right, or that's equal to negative RT ln KEQ, so you can solve for your KEQ. So it's a simple math rearrangement here. KEQ would be e to the negative, so delta G naught over RT, we've shown this before, and negative delta G naught is just positive NF, each standard cell potential, over RT. Let's look at an example. Let's look at the standard reduction potentials and calculate the KEQ for this reaction, and then we'll try to calculate the KEQ using the standard Gibbs energy of formation. All right, so let's break this up into two half reactions. You have iron plus 3 going to plus 2, Okay, that would be reduction, and iodide going to I2 would be your oxidation. So let's look at this half reaction right here. 2I negative, 2 iodide ions gives you I2 solid. So that means you need 2 electrons on the right hand side. This is your oxidation. Okay, this takes place at the anode of your galvanic cell. And your reduction here would be iron with a +3 charge, gives you iron with a +2 charge. Okay, and you need an electron here to balance it. So that's reduction. Iron +3 gains an electron to give you iron +2. This is your cathode reaction. So this reduction occurs at the cathode of your galvanic cell. Since electrons lost, mass balance, electrons gained, this will have to happen 2 times every time the anode reaction happens. Okay, so that will give you your overall reaction. So let's look at the standard reduction potentials for these half reactions. So let me do a search on Google. Standard reduction potentials. There you go. Okay, let's see. Have a bunch of standard reduction potentials you can look up. Let's just, this one's a good one. Alright, so from this one I can look up for iodide to I2. Here. Let me zoom in on this one. So many places where you can find this information. I2 solid gives you 2 iodide. That's reduction of I2 solid to 2 iodide is plus 0.53. Okay, so the standard reduction potential for that is plus 0.53. So the standard oxidation potential would be negative 0.53 for this one, since it's reversed. Okay, and the standard reduction potential for this one, since this one is the one that undergoes reduction, iron +3 to iron +2. Let's see, where would that be? Iron look at the alphabetical listing here. Okay, iron +3 to iron +2 is positive 0.771. Okay, so that's 0.771. So our cell potential is just equal to 0.771. Remember, cell potentials are intensive properties, so you don't multiply this by 2. Okay, so 0.771 volts plus negative 0.53 volts, or you can say minus 0.53 volts if you want to just, you can say E right, E reduction minus E plus E oxidation. But remember, this is the negative of the reduction potential of the anode reaction. Okay, so either way. So this is going to be 0.771 minus 0.53. 0.771 minus 0.53. That's 0.241. So this is 0.241 volts. Alright, so if that's the case, how can I calculate KEQ? What's the formula for KEQ? E to the NF E naught over RT, where N is 2. Okay, you have 1 mole of this reaction, as written, will involve the transfer of 2 moles of electrons. So let's do that on MathCAD. So I'm going to say KEQ equals E to the negative, E to the N F, 96,500. E is, what was E? 0.241 volts. 0.241. Oops. Over RT. Okay? And Fe naught over RT. So over R, 8.314, temperature 298 Kelvin. So KEQ in this case is 1.42 times 10 to the 8. Okay, so finally, let's calculate the KEQ based on the delta G of the reaction. So what you're going to need to do is calculate the delta G. Look up the delta G of formation, okay, from a table in your textbook. So delta G, standard delta G of this reaction is equal to delta G formation of the products, which would be 2 times the value for ion per mole, okay, plus iodine would be 0, right? That's iodine would be 0. That's an element in a standard state, minus 2 times the standard delta G of formation of iodide ion in aqueous solution, minus 2 times the delta G, standard delta G of formation of ferric ions in aqueous solution. Okay, and that should be a straightforward calculation. Once you've gotten your delta G, then you can calculate KEQ just like before. Is e to the negative delta G naught over RT, and you should get essentially the same KEQ value. I'll leave that up to you to figure out. Okay.